All right, so we continue our lecture. Right, hopefully everyone can see this screen, this slide, okay. All right, so back to our discussion. So what is actually sequential circuit? So sequential circuit has the elements of the output depends on the current and also the previous input. So this is a very important. If you define a sequential element, you need to have this keyword. So what is actually current and what is actually previous input? So just look at this example. We have a finite state machine, and the output, which is this one. Okay, the output is depend on the current. So current is actually your current input is in. So this is your current input, and your previous input is actually the feedback here. So the element of feedback here is actually temporarily store the data or the token. So this is actually done by either a flip-flop or a latches, and that's why we have what we call a sequential circuit here, or sequential elements here, which is a flip-flop or latch. But in this case, this one, okay, this block, okay, either flip-flop or latches, it will temporarily hold the token, and then they will pass back to the input. So this is actually your previous input. You join with your current input, okay, previous input and current input, and get the output. So this is actually the characteristic of finite state machines. All right, okay. So another example is actually pipeline, okay, pipeline. So pipeline is actually another example of sequential circuits. All right. So if token moves through pipeline at constant speed, so no sequencing element would be necessary. Okay, so the sequencing element, so you have to remember the purpose of sequencing element is to make sure that the early token that arrives early and the late token that arrives late, it's what we call it, it's ready. It's ready for operation. Okay, for the operation. Okay, for the data operation. Okay, so it will make sure that the early and also the late token can arrive at the same time at the input of a system. Okay, for example, I think we have discussed last time. So we have an adder here. Okay, and then we add, and then we have another adder, for example. Okay, so we have input number 1, number 2, number 3. Okay, so how do we make sure that input number, for example, here, number 4 and number 5. So input at number 4 and number 5 arrive at the same time. How do we make sure it? So theoretically, if you can see here, so let's say this is your system, okay, from the outside. We have delay inside the first adder. Okay, maybe I use different. So this is your first adder. Okay, and this is the second one. Okay, number 1, and this is number 2. Okay, so A1, adder number 1, and adder number 2. So output of adder number 1 will take some time because there is a delay inside the first adder, inside the adder A number 1. So the input from 3 is directly enter the second adder or A2. And clearly, so the delays between this path and this path different. Okay, so the path from that goes through the first adder delay is more than the direct line here. So of course we need to have a sequencing element here, okay, to make sure that, okay, sequencing element here to make sure that the data arrive here same as here. Okay, so that's actually the one of example, the purpose of having sequencing element. Okay, all right, so example, fiber optic cable. So light pulses token, we call it as token, are sent down cable. The next pulse sent before the first reach. Okay, that's actually an example of what we call as of a pipeline. Okay, so this is the cable. Okay, okay. So you send the first path here. Okay, after certain period of time, okay, certain amount of time, it will become here. Okay, maybe this one T number 1, for example. This is T number 2. T number 1 here lah, T number 2 here. Okay, sorry. Okay, so the path you send from here and then reach at the end. Okay, you can send multiple times, but in different interval of time. Okay, so once you send maybe the path is here, and then after a certain amount of time, it will be at T number 2, and then during the T number 2, you will send another path. Okay, which is next path lah. Okay, next path send before the first reach the end of the cable, which is here. Okay, so that's actually the concept of pipelining. You send one after another. So that's what we call a wave pipelining. Okay. Okay. So normally we delay fast token lah. Okay, so that we will get the information arrive at the same time. For example, this case lah. Right. Okay, so this is actually an example of the difference between latch and flip-flop. So have a look on this. Okay, the diagram and also the timing diagram, the block diagram and the timing diagram. Can you identify what's the difference between latch and flip-flop? You focus on maybe on the timing diagram. So here we have clock. D is actually the input. So clock, okay, D is the input for latch, and clock and D is input for flip-flop. Same, almost the same. Okay, so what's actually the difference in terms of the output and in terms of the diagram? So can anyone answer? You can use a chat box, or you can unmute your microphone. Any response? If no response, I will leave this for you to do and to figure out on your own. And when you get the answer, and then we discuss later. Any response? It's okay. Incorrect response also okay. Don't worry to make any mistake. That's a learning process.
Can you repeat the question? Sorry.
Oh, what's the difference between the output of the latch? I mean Q lah. What's the difference between the Q latch and Q flop? Can you identify the difference and explain? And that's the question lah. If you cannot explain, it's okay. At least identify the difference and let me know lah. That also okay. What's the difference? So maybe I explain further.
Sir,
Yeah.
the latch is triggered when the input is having a positive edge triggered or negative edge triggered, and flop just follow the clock. Clock's input positive edge triggered.
You mean positive for the latch? You mean positive edge or level?
Both, sir. For it follows for the clock and the input, the D input.
Okay, partially right. Okay, partially correct. Good, thank you. So the answer is, if I can recap the answer, so the output depends on the input, okay, D, which is D, and also the clock, okay, correct. But in terms of the edge triggered for latch, maybe need someone else to what we call to support him. Any? Any answer? Any other answer? No answer.
There is
So,
an answer.
okay.
There is an answer.
Okay, thank you. So actually, as we can see here, latch,
Chat box.
sorry,
Chat box. Ada.
oh, in the chat box. Okay, thank you. Flip-flop block diagram have 8. Okay, correct. Riz Mukri mentioned that flip-flop is age triggered, latch is level triggered, yes. But I need what we call a more detailed explanation. Okay. And then thus inform that the flip-flop is age triggered device that copies D to Q on the rising edge of the clock and ignores this. Yeah, correct. That's correct. That's for flip-flop lah. Okay. So maybe I can copy this, okay, and then explain in the class. I think this standard definition I found somewhere else, but it's also good lah. We have to have response. Okay. Right. To make the font standard. Okay. Okay. All right. Okay. The flip-flop is an age triggered. Okay, this is an important word. Age triggered means that it's either rising edge or falling edge. Okay. Copies B to Q. So input become output. And that's actually what it means by copies B to Q, right? On rising edge of the clock. Okay. So that's what we call as edge sensitive. And we mention here, okay, age triggered or age sensitive for a flip-flop. Okay. Of the clock. Okay, so clock is actually the reference signal, okay, for the D flip-flop or for the flip-flop to produce an output. Okay, and ignores these at all other time, means that other than rising edge of the clock, okay, Q will equal to D. Q will not equal to D. Q will follow its previous value. Q will follow its previous value. Okay, example. An example. So maybe try different color. So just focus on the Q flop. So Q flop is actually the output of this. Output of this. This is flop, this is latch. So now we focus on the flop first. Okay, and the output of the flop is this one. This is the output. Okay, so this is the input. So the input is low, on the rising edge of the clock, which is this one. This is the rising edge of the clock. Okay. So, and this is another rising edge of the clock. So these two is actually the triggering point or the triggering edge that will copy D to become output. And that's why you see here, okay, when you extrapolate here, so D equal to 0. And that's why you see output equal to 0. Okay, until when? So until it sees the next rising edge, which is here. So next rising edge, D equal to 1, you see? And then only after you see the next rising edge, okay, and then it will update D equal to 1. Okay, other than that, although we see D equal to 1 here and 1 here, it will not update Q because during this time, okay, and this time, no rising edge happen. Rising edge only happen here and here. Okay, understand? Huh? All right. Unlike the latch is level sensitive. Maybe we use different color. So So latch is level sensitive. Okay, level sensitive means that it will transparent. Okay, copy the D during the level. So in this case, the level, as for example, we assume is sensitive to high level. Okay, high level of the clock. Okay, so it means that it will copy whatever input during the high level, and that's why you can see the latch. It will copy it, all of the output, copy the input. You see the same. Okay, until here, although the input is high, it will not copy because it's active low here. It's 0. Okay, level 0. It will not copy it. It will remain its previous value. So in this case, its previous value is 0. So it will remain the previous value until it sees the next level, next high level, which is during this time is high, and then this one will copy. If that's for a latch, okay. Compared to the flip-flop, it's different. So flip-flop is edge triggered. So in this case, rising edge trigger. So only during the rising edge it will get the output. Okay. Other than that, it will continue the previous value of the output. In this case, 0 1. So it will continue 0. Okay, 0 until next rising edge, which is here, and then it sees 1, output 1, and then it will go high. All right. Okay. If you have any question, just let me know. Okay, thank you for those who have responded. Okay, thank you. Kamini, Haris Mokri, Das, and also Redman. All right. So sequencing overhead we have discussed. Okay. Okay. So normally we delay. Actually, we delay the system lah, okay, to make sure the data arrive, both of the data or the input data arrive at the same time or acceptable time, and then that will introduce delay. Okay, and then that's actually add some delay to the token that are already critical, and this will decrease the performance. Okay, for example, F lah, our frequency, F equal to 1 over T. Okay, when we delay that time, it will increase the T. When the T become bigger, okay, when the T become bigger, and then F will become lower, and then performance will become slow. Okay? Some people call this clocking overhead. Time clocking. To detail, you may read the textbooks. Okay, so to see the what we call operation of latch, how latch and flip-flops store data temporarily, how it happened, we can see internal architecture of the latch itself. Okay, so basically, the initial design of latch in 1970, okay, it was made from a pass transistor. Okay, so this is actually a pass transistor. Okay, remember latch, we have D, okay, then we have Q, and then we have a firing signal, what is actually we call clock lah. Okay, clock lah. So normally clock. Okay, like this one lah. Okay. So Q will become an output. Okay, if this enable the data to transfer. Okay, depending on the clock lah. Okay, for the case of latch, every high level of the clock lah. Okay, or low level of the clock. This is high and this is low, depending on the designer, right? So this gives you the advantage, compact and fast, and the limitation. We have lots of limitation here. So during the early design of the latch, okay, and then people start improving it. They use transmission gate, whereby we have another transistor here instead of only one transistor. Okay. And then they have advantage of positive side, no threshold voltage drop, but it requires inverted clock. Okay, inverted clock here. Okay, and then people invent another latch, which is comprises of buffered output or inverted output. at the output side. They have Q bar here, okay, and also Q bar here for the case of inverted input. So here inverted output or buffered output, here is buffered input. Okay, two design of latches. And then no feedback loop. For this one, no feedback loop. And then people or designer improve it. Now it has another feedback loop, which is this one. That's make the latch has a memory. Okay. Has an inverter feedback. Okay. And this is actually, as we go down there, we have the final design of the latch. Okay. Inverted. We have the transmission gate, and then we have also the buffered output here. Inverted output. All right, and this is we call as a feedback, right? Okay. So we can see the advantage, smaller and faster, and the limitation or disadvantage, it has unbuffered input. Okay, this is the input. Okay, this is actually the final design of the latch. If you can see the latch like this one, okay, D, then Q, then clock or phi, and the internal diagram of this is actually this one. We have this inside. Okay, for the case of flip-flop, the internal design is actually a duplication of this portion. Okay. You see the design. Okay, it's actually the duplication of this portion. Now you can see it clearly when I circle it. Okay, back to back. Okay. Right. That's what we call as a flip-flop. Okay, so to understand detail, you can refer to the textbook. All right, it's explained in detail in terms of the operation of the flip-flop. Okay, so basically, as we can see here, both latch and flip-flop has a feedback loop. Okay, has feedback loop, and that's why they can temporarily store the information, right? And that's why you can see here, and in terms of timing diagram. Okay, for example, latch after after the high level of the clock, it will continuously store this information, store the value of 0 until the next high level. How this stores the values is inside the architecture of the latch. Okay, similarly for your flip-flop, you can see here all of this data is actually temporarily stored in the flip-flop. Okay, until it sees the next rising edge. Okay, so during this delay, okay, during this time, so any late arriving signal or early arriving signal will become acceptable if they fall between this delay for the case of flip-flop, between the first rising edge here and the next rising edge, which is this blue line. So any late or early arriving signal that arrive between this time is acceptable. And that's why you can see the effect of frequency when the what we call the clock period here, T. Okay, maybe I can sketch different one. Okay. This is a clock. The clock period is actually the repetition of the pattern. Okay. So this is a T. When we increase the T, okay, to become, for example, your clock getting this one. Okay, we increase the T, and then we will allow more time for the late arriving signal. So this is, let's say, T1, and then this is T2. Okay. Late arriving signal can arrive anytime within this range, T2. However, in terms of frequency, so F for T1, so F1 we call is in this F2. Okay, so F1 greater than F2. So that's actually reflect the performance. Okay, the more the delay we add to allow more data to arrive, arriving data to arrive, and then the lower the performance of our system, the lower the frequency of our system. All right. Hope everyone clear on this. So in terms of the architecture or design inside the flip-flop and the latch, we can see here, and then what is actually make the element, sequencing element, either latch or flip-flop, able to hold the data. Okay, they have what we call a feedback loop that temporarily hold data. Okay, same as the flip-flop. Okay, flip-flop got two feedback loop. Okay. All right. So we have also what we call latch. Okay, latch and also flip-flop with enable. Okay, this is actually without enable, with enable, and the previous one without enable. Previous one without enable. So what is the purpose of enable? So enable normally we use in what we call a low power design. Okay, just imagine we want to turn off some block in our design, in our chip, to make sure that the chip consume less power. So how to control it? We have a enable button or enable input. So the enable input, will either enable the input D become an output or not. Okay. All right. So we call it clock gating lah. So increase in setup time and so on. And another thing is actually in a marks lah. So we have example here in a multiplexer design. So we have enable here to do a selection between 0 or 1. Okay. If we select 0, and then the output will be based on 0. Okay. If we select 1, the output here will be based also on D. Okay. For the case of the clock gating, the enable signal is actually, so this is actually a clock. This is normally clock, CLK. So we have clock running non-stop normally. Okay, but if you didn't enable the clock, okay, this is AND gate. So AND gate, so if you give 0, so this is the waveform of the clock. Sorry about the diagram. Okay, so if we give 0, 1, 0, you get 0 lah, because AND gate. Okay, 0, 0, also 0. So towards the end, you will get 0. But if we give 1, okay, if you give 1, let me use different color. If you give 1, if you give 1 for the firing, for the clock lah, this one, okay, and then you will get the actual, you will copy the clock. Okay, if you give 1, you will get the clock, which is right. Understand? Similarly for your flip-flop. So that's actually the purpose of enable in the flip-flop and also latches. We also have reset, okay, because in our design, if you remember, we have discussed in digital IC design, EMT NMJ 32303, okay, about synchronous and asynchronous. Okay, synchronous and asynchronous. So in terms of what we call architecture inside the latch, okay, we have another input here called reset. Here is actually the reset. We have another additional gate, okay, additional NAND, 2 input NAND gate, right? That will reset the latch or the flip-flop. Okay, similarly for your flip-flop, right? Okay, detail of the architecture, you don't have to worry. At least you understand the difference between latch and flip-flop, and then how they hold data in terms of architecture, and then in terms of the timing diagram. Okay, any question? No? Okay, so we almost 1 hour lecture. So this is actually an exercise for you to do, okay? If you have face-to-face class, and then we will do quiz lah. But for the face-to-face, for the online, maybe it's a bit difficult lah, right? but you can try on your own this one. You should be able to get the answer because we have discussed this already. You try to read on your own. All right, so actually we have static circuits and also dynamic circuits lah. Okay, these have been discussed in our in your I think digital two lah, digital two. You learn this static CMOS circuit and also dynamic CMOS circuit. What is actually static? What is actually dynamic? Um, so static CMOS circuit basically like your conventional static CMOS logic, okay, um, logic gate and so on lah, right? So that's actually we call as static CMOS, okay. Your pass transistor that we discussed just now, transmission gate logic, okay, also fall under static CMOS. Okay. For the case of dynamic logic, okay, domino logic is an example lah that. So in summary, okay, so dynamic logic, dynamic CMOS logic, actually logic that use clock, okay, and static CMOS logic, they didn't use a clock, okay. For example, AND gate, NAND gate, and so on. All right, so this very important topic, sequencing method. Okay, before we go to this, I like you all to read the textbook on page, I think, yeah, this one. So that diagram is actually taken from this textbook lah. Okay, if you can see, okay, flip-flop, two-phase, transparent latch, and path latch. You go back, they are the same lah. Okay, the same. So I give you time to read this one, this page. So page 404. Okay. You read this first. I give you maybe about 5 minutes break, and during that break, you read this, and then we shall discuss after come back. Okay. Any idea? Have you found any idea based on the reading yang membantu ataupun tak? Or need explanation? Just focus on the flip-flop first, okay? Don't look at the two-phase transparent latches and path latches first. You look at this one. So basically, so this is actually the detail, okay? So we can see here, maybe I can sketch something. This is actually first rising edge of the clock, okay? And this is another rising edge of the clock. So just focus on it first. As we discussed last time, just now, okay? Flip-flop is actually edge sensitive, okay? So we have two flip-flop here, one at the input of a combinational logic, we call SCL, okay? And the other one is the output of the CL. So this diagram looks like a pipeline stage, as we discussed just now. Okay, so the data that arrive through the first flip-flop, the incoming, the input flip-flop here, okay, will be become an input to the okay, sorry. It looks like someone want to join, but I cannot see. Okay. All right. So, so when the input goes to the flip-flop, okay. So that data, okay, will be will go through the sequencing process actually, okay, and then the data that arrive early, okay, will wait for the data that arrive late. Okay, similarly to the concept of the sequencing element of combination logic or static circuit. Okay, so and then when it get all the data ready, okay, during the rising edge of the clock, and then it will pass to the combinational logic. Actually, this is actually the time TC, we call it as TC. Okay, the time, the clock period, okay, that allows the data to be computed using the combination logic, and then until it reaches the output at the next clock, then it will get the output. Okay, so I think the explanation is in here. You can read here. Okay, this is we can start from here. Okay. The horizontal axis corresponds to the time at which a token reaches a point in the circuit. For example, the token is captured in the first flip-flop. So we have first flip-flop, this one. Okay. On the first rising edge of the clock, which is this one, first rising edge of the clock. Okay. It propagates through the combinational logic. Okay. Okay. Data is captured here on the first rising edge of the clock. Okay. And then the data is propagated. Okay, once the data ready, okay, it will propagate to the next block, which is the combinational logic. Okay, through the combinational logic and reach the second flip-flop on the second rising edge, which is this one, second rising edge of the clock. So the dash vertical line indicate the boundary between one cycle and the next. So this is actually one cycle, as I mentioned to you, TC. Okay, and the next cycle is after this. Okay. So that's actually the process. So within the one clock cycle, okay, so the data is computed here and then passed to the next flip-flop, which is the output. Okay, I think inside the lecture note we also have. Okay, so this is actually the summary, the point form, the point form we actually extract from the text. Okay, all right. So if the token advances from one cycle to the next rising edge of the clock. So if a token arrives too early, and then it will wait at the flip-flop until the next cycle. So that's actually the process. Okay. So detail, you can refer to the textbook. Okay. So flip-flop based system use one flip-flop on each cycle boundary. So which is this one. This is flip-flop based system. Okay, so one flip-flop, one each cycle boundary. So this is one cycle boundary, and this is another one. Okay. Token advance from one cycle to the next rising agent. If a token arrives too early, wait for the next. Wait at the flip-flop until the next cycle. This is actually already mentioned in the slide. Okay. So one of the most important thing here is actually recall that flip-flop can be viewed as a pair of back-to-back latch. Okay. Remember we have discussed this. Okay. Flip-flop is actually we have two combination of latch, okay, back-to-back latch, okay. So then by that assumption, so we can call the flip-flop as having two half cycle of that latch, okay. So first half cycle, one latch, and another half cycle, another latch. So that's actually give a complete cycle of the clock for the flip-flop. Right, so this is actually the detailed explanation. Flip-flop can be viewed as back-to-back latch pair. Okay, back-to-back latch pair. Okay, don't worry about this one. Okay, so the important thing is actually the definition or the terminology here. Okay, maybe I can zoom a bit. Okay, in our lecture note also we have this. We focus on the flip-flop first. These two we skip first. Okay. This one. Okay. TPD. Okay. So we have P here is actually stand for propagation. Okay. And C here is actually contamination. Okay. And P here propagation. Okay, that's how you can remember. Okay. And C here, the first C is actually contamination. P here, propagation and so on. Okay. And the first C also contamination. So D here stand for delay. Okay. So TPD is actually logic propagation delay. We focus on the combinational logic. Combinational logic inside the block here. Inside the block here. Okay. So TPD stand for logic propagation delay. TCD stand for logic contamination delay. So what is actually the difference between propagation and contamination? Okay, let's have a look. Okay, so propagation delay, okay, is amount of time needed for a change in the logic input to result in permanent change in the output. So the keyword is permanent change at the output. Okay, permanent change at the output. Okay, here, this one. Compared to contamination delay, okay, this is actually an amount of time required for a change in a logic input, same as the above, okay. Only difference is to result in initial change to the output. So the rest equal. So the difference is permanent change here for the propagation delay, and contamination delay is initial change. Then how do we see it from the timing diagram? Okay, so let's have a look at the timing diagram. So this is your timing diagram. This is a input of a combination logic, and then Y output of a combination logic. Okay, so A actually from A to the output, okay, initial output change. So this is actually an output, and this is actually what we call as invalid data. Invalid data, and this is actually a valid output data. Okay. So just assume this is maybe an inverter, for example. Okay, so we can get the output of an inverter. For example, we give 0 and then we get 1 here. So 1 will start here. Okay, so in between here, okay, in between this is actually invalid data, either 1 or 0, invalid data, unstable data. So, and here is really a previous data. Okay, so TCD, okay, contamination delay time, is actually initial changes at the output. So this is actually reflect to the initial changes to the output, and TPD, or T propagation delay, is actually a permanent change of the output, whereby here For example, we have logic 1. Logic 1 permanently changed, is not changed to 0 or fluctuate to any value. So it's permanently changed. So that's what we call as propagation delay. So normally the propagation delay is actually time for the input to travel along the combination logic until goes to the output. That's actually the basic. It means that the time from here, okay, from here, okay, basically from here to here is actually the PPD. So what's actually the delay time in between the input to the output of the combination logic. Okay. All right. Hope everyone clear on this explanation. If you have any question, just let me know. Okay. So that's about the propagation delay and contamination delay. P stands for propagation, C stands for contamination. So the next one is actually TPCQ. So we know that P is actually propagation. So CQ. So remember your clock, okay? Clock C, and then your output Q. Okay, and then this is your D. Okay, the either flip flop or latch lah. Okay, decapitulator or whatever lah. Okay, you remember the diagram? Okay, yeah. Okay, C, Q, and D. Okay, so that's actually reflect to that lah. Okay. TPCQ, so C is clock, Q is output. So clock to Q, okay, either latch or flop, okay, depending on the diagram or the clock. Okay, so clock to Q propagation delay. Okay, so clock to Q propagation delay. So if you see the the next one, clock to Q continuation delay. Okay, so let's look at this one. The CQ, okay, contamination delay, and PCQ. See, okay. So as we discussed, so contamination delay normally initial change at the output. Remember that, same as this one. Initial change at the output. Okay. In this case, CQ. So from C, from clock here to the Q. Okay, to the Q. From clock to the Q. So same as TPCQ. Okay, TPCQ from clock to Q to output, but for permanent change of the output. This is initial change, contamination delay. Propagation delay is permanent change. So that's actually the difference. And the difference between combination logic and also flop is actually flop got clock lah, and combination logic, as we can see here, no clock. And here we have clock element, and that's why you have CQ and CQ as well for contamination delay. And this one only CD and PD. Okay, all right. So hope everyone clear. And we have another two definition for flop. Okay, which is setup time and hold time. So we can see here the diagram. Maybe I can make it smaller. Okay, setup time and hold time. So we can see here this is a clock. Okay, and this is the rising edge of the clock. Okay, this is ideal clock. Okay, so normally a clock need to have setup time and hold time. So what is setup time? What is hold time? So we can see the dotted line here, which is the boundary between the rising edge and also the between the rising edge 0 and 1. So this is 0 and this is 1. So the boundary in between the 0 and 1, okay, so a time required, okay, amount of time of synchronous input D, okay, must be stable. So D, input D, this is your flip-flop, input D, and this is your clock, C, L, K, and this is your Q. So it's mentioned here, amount of time of synchronous input D, so D here, must stable. So that's actually the T setup. So that's actually the required time for the clock. Okay. Before the active age of the clock, means that your D input here must be within this time T setup. Okay, that's actually the amount of time lah. Okay, more is okay lah, but less cannot. That's actually the minimum amount of time lah. You have to make sure that your input data is stable during this period of time, this data, before it can be used as output. Okay, stable output. Okay. All right. So the whole time, usually amount of time, which is this one, whole time, amount of time the synchronous input must be stable. It means that after rising edge of the clock, just after rising edge of the clock, the input D must be stable. Okay, remain the previous value. Okay, like this one. D remain the previous value during the T setup until end of T hole. And then after that, D can change. See? D can change. And before that, T setup, D also can change. But during the setup time and hold time, the input D must stable. They must be the same value. Senang cakap. Right? Must stable. Cannot change during the setup time and hold time. Okay, if you remember your lab, maybe you can go back to your lab after this and then you check what's actually the setup time and hold time that you set in your lab, okay, your lab multiplier or whatever design that you have done. And then based on the report generated from the synopsis, and then you can explore further in terms of the timing information, where is the setup time and where is the hold time, how much is the setup time and how much is the hold time. All right, so the key difference is actually before and after. So what actually means before? So this is before the rising edge of the clock. Okay, and after, which is this one, after rising edge of the clock. Okay, after rising edge of the clock. Okay, before and after. So here it mentioned the active edge. So active edge means that either rising edge or falling edge. Right. Any question? Ada soalan? We have also another delay we call as wiring delay or routing delay. Okay, we check in your report lah, synopsis report. So we have discussed this, setup time and hold time. And when we finish it, and you should be able to analyze this lah. So for example, if I give you, if I ask you to explain about the timing diagram, okay, for example, on combinational logic, we have this GCD and TPD. On flip-flop, we have this setup time and hold time, and also TCCQ and TPCQ. You should be able to explain. Okay, for the case of latch, okay, it's a bit complicated lah. Okay, but you can explore on your own. All right, this is an example of exercise that you can use during the 1 hour asynchronous lecture tomorrow. So tomorrow you try to do this question. Okay, we have actually 2 exercises already. Exercise number 1 on the timing diagram, which is this one. Okay, exercise number 2 is on the definition of this explanation. Okay, explain sequencing method using flip-flop. Okay, transparent latches and pulse latches technique. So this you can get from the textbook and try to explore. Use an appropriate timing diagram for each of the techniques. Try to explain using your own words. If you use your own words, and then you will gain more understanding on the section that you are working on. Okay, so the number B, okay, the second one is differentiate between static and dynamic. I think this is a lot of information available. Okay. All right, so how do we determine the maximum delay? So the maximum delay is very important for you to determine the what we call as the clock frequency. Okay, let's have a look on this one. So this is actually the same diagram as before. So we have a clock, okay, first rising edge and second rising edge. Okay, and we have what we call the diagram, combinational logic, and we have a flip-flop, F number 1 and F number 2. So Q output, Q1 of a flip-flop 1. D2 is the input to the F2. What happened? So we can use the timing diagram to explain. Okay, so Q1 is actually the output from F1 will become stable output. See, stable output when we have what we call here TPCQ. P stands for propagation, C to Q is actually from your clock here to Q1. Okay? So that time is actually from this clock to the here. So the first what we call a permanent output to the permanent output. Remember propagation and contamination. So propagation delay, actually permanent output change. So that's why you can see it's permanent change. Nothing happened here lah. So let's say this is represent value of decimal 10, for example. So it's continuously 10 until the end. Okay, but here it's actually uncertainty. Okay, uncertainty value. Okay. And TPD actually is actually from the first time of the permanent output of Q1 until D2. Where is D2? This one. Okay. The time is travel from this location to this. So that's actually the TPD. And TPCQ is actually happen inside this. Okay, clock to Q inside the flip-flop. TPD is inside the combinational logic, and T setup is actually inside the flip-flop, the second flip-flop. Okay, for the output, for the input to become stable. Okay, for the input, D become input to the flip-flop number 2. So D must be stable between this time, from here until the next rising edge of the clock. Remember that we have discussed about this diagram, similar to this one. Okay, that's actually the T setup, the rising edge of that clock, and the time before it, there is a setup time. And time after it is actually the hold time. Alright, and that's why we call this setup time. Okay. So you can see the various combination of data in the two flip-flop F1 and F2. Okay, for the case of latches, two-phase latches, you can explore it later. Okay, so in terms of equation, okay, for the TC, okay, this is TC. TC clearly you can see it equal to TPCQ plus TPD plus T setup, and that's why you see TPCQ plus TPD plus T setup. That's actually the total time for TC. Maximum time for TC. So to get frequency, normally we have F equal to 1 over TC, whereby TC is actually the summation of all delays from PCQ, PD, and T setup. And that's actually we determine the frequency of a system. Okay. So previously in your study, okay, we have discussed about this one, right? You see this, the clock, then the TC is actually from here to here. This is the TC. Okay, but for detailed one is actually TC is actually we include the PCQ, okay, because we have the element of first flip-flop, and then TPD, the delay between the inside the combination logic, and also the setup time before we enter the next flip-flop. Right? Okay. This is an exercise. Okay. We have about half an hour, okay, before we finish the lecture. So I give you time to do this exercise. Okay. The question asks you first. So this is actually a diagram of Itanium 2 processor. Okay, Itanium 2 processor. They have an ALU here, data path control, bypass control. Okay, register file and so on. Okay, we interested on this block. Okay, the what we call the red block, and then we expand it, zoom it. This is actually the element inside the block. We have flip-flop, okay, and all the combinational logic, and then it feed back to the flop again. Okay, you also given a delay, propagation delay, and also contamination delay in the form of picosecond delay. Okay, adder. So this is an adder. Where is the adder? Yeah, this is an adder. Okay, the propagation delay of the adder and the contamination of delay of the adder, and then we have result marks, We have early bypass mark, this one. We have middle bypass mark, and we have a late bypass mark, and we also have wire delay. They also mention wire delay. Okay, wire delay 2 millimeter wire delay, and then here we have 2 millimeter wire delay. So two wires delay, they model as two wires delay. Okay, the question asks you the first one, identify the critical path. So to identify critical path, you mention what are the components involved in the critical path. Okay, adder, mark, and so on. Okay. The second one, calculate the critical path of the unit. So to calculate this must be based on number one. And the last one, calculate the minimum cycle time. Okay, given the other time as here. So try to use this time to answer this question, and then we shall discuss after you all finish lah. So if you finish earlier, and then we shall discuss today. If you not finish early than expected, then we discuss in our next lecture. Any question before I give you time to answer on your own? So try it on your own. Any question?
Tak ada doktor. Doktor, page apa tadi?
Ini Wednesday you can go to textbook lah. Ini page, this one maybe not tally with the one that you have lah. Okay, you can go to Wednesday. Okay, or you can refer to lecture note first. Okay, don't go to Wednesday. Refer to lecture note first. Okay, try to understand whatever we have discussed and try to answer it. Okay, I give you all time before maybe around 15 minutes, 15 minutes. Okay, we can discuss. Okay, so any of you managed to get the answer? Or we discuss next week?
Saya tak dapat, Doktor.
Huh?
Saya tak dapat.
Tak dapat? So need more time to explore. Huh?
Ya, Doktor.
Okay, so I give everyone more time to explore. So we shall maybe discuss next week lah. Maybe dah penat kot. Okay, so I like to remind again on our test will be, so I share the attendance form already shared in the chat box. So our test will be on next week, Friday, 9 to 10. So we'll start 8:45 to 10. Okay, so 8:45. Why? Because I want to allow you more time to prepare, because we do it online, so need to upload and so on. Okay, so I will stop the recording first.